simple. And this slide shows relative resistance change of palladium being charged by hydrogen. And this can be done relatively simply. You don't have to weigh samples. You can take them out and measure their impedance. I'd just like to point out a couple of factors. When the material becomes saturated, if the current is reversed, you can go into what appears to be a supersaturation region. And this could be related to deuterons or deuterium-deuteron equilibrium within the sample changing. There's also been Hall measurements made now of these materials, and I'd like to stimulate people to try to make measurements combining impedance measurements and, say, deuterium concentration by either neutron scattering or Hall measurements.
Thank you. Got another question, Steve Feldberg. The lady's coming.
Yeah, this question is addressed to Kevin or any of you folks who've been analyzing for the tritium, which is a rather fascinating observation. What would be the effect of H2O2 word in the solution on that analysis?
You want to answer that?
No, I don't, okay. Quite frankly.
Just checking. Peroxides, hyperchlorites, bleaches, as well as hydroxides drive these scintillators crazy. It pumps them up, makes them much more active for chemiluminescence. Of course, it's not an infinite time. It just means you have to leave these things in the dark longer to die out and be aware of the problem. And there have been scares, errors made in health physics in this type of counting where they thought, my God, the world is coming to an end. We're contaminated with tritium. Okay, but you do have to be aware of that. Does that answer your question?
Well, the question, of course, the real question is, did you take precautions to avoid this? It's
right.
Not unreasonable that peroxide might be in a solution.
It's quite reasonable, and yeah, I mean, in my own lab, I left samples in for days in the dark, and monitoring, you know, if there's any change in the activity level, and monitoring the beta spectrum quite closely.
Okay, yes.
To Professor Bachris, what was the difference between cell A and cell B?
The amount of exposure time. The one with the greatest tritium was exposed for something like 4.5 weeks. That exposed means constant charging at 60 milliamps per square centimeter. And the cell with the lower tritium was charged for a lesser time, and I'm not sure how much. I think it was 3 weeks. You?
My question is also to you, Professor Bachris. Given your comments earlier, in general in chemistry or electrochemistry, it's accepted that if we have the law of mass action, which dictates that if we have A plus B goes to C, as we raise the activity or the fugacity of either or both reactants, A or B, we generally drive the reaction to the right. Do you believe, my question is, do you believe that that same chemical sort of viewpoint would apply at all to a nuclear reaction of deuterium plus deuterium at high activity, 10 to the 12th, forcing a nuclear reaction of helium-3 or helium-4?
Well, I'll say my own common sense and intuition says yes, but I'm not really qualified to answer it by experience. Is that a Dr. Wolf question? No? You.
Stan Lockhart from MIT. I have a general question about fusion product measurements in these experiments. You know, we've heard a lot about positive and negative results today, and I think that's kind of a digital way of reporting the results. It's not quite correct. The real question is a quantitative one about how much fusion reaction power is really going on in these experiments. So I'd like to direct this question to anybody who has claimed to measure fusion reaction products. I hope we will always state how many trillionths of a watt of fusion power is being detected in the experiments, and the real question is, can the excess heat be accounted for by the fusion power production that you can calculate from the fusion products? And I think that's kind of the whole question that we'd like to answer at this conference.
No, I agree with you, and I think that if we could answer that question clearly, we'd be much further ahead. If I may give an answer myself to this question, I have never said at any time that I was measuring fusion. I always refer religiously to the Fleischmann-Pons effect. I don't know whether fusion is taking place at all. We do see, as I like to call them, nuclear particles. Of course, I mean principally neutrons and tritium. Whether those things are connected with the heat is the central question of the whole field. And only one person whom I know has made a clear experiment which says yes, or it says anything at all about it. Very unfortunately, he didn't get to the meeting. He was, however, at Los Angeles last week. His name is Grotti, G-R-O-T-T-I, and he comes from the University of Rome. And he told me the following. He said he took palladium sponge. He annealed it, I think it was for 100 hours in very high vacuum. Then he started electrolyzing. He got nothing for about 40 hours. And then both heat and neutrons switched on at the same time. He said that the neutrons were about 100 times background. He didn't define the heat quantitatively to me.
He detected the neutrons as BF3.
My memory is, I can't be sure it was a corridor conversation, but I believe not.
Well, I think there, just to follow up on this question a little bit, it isn't really uncertain that fusion reaction of a particular type is not taking place. For example, if you see a neutron count rate of, say, 40 neutrons per second, then you know that the heat you're observing cannot be due to that particular reaction that has the neutron channel.
Yeah.
So it can be crossed off the list.
Yeah.
And so the question is, you have a list of reactions that are possible. We know, can write down every possible reaction, and we can go through and cross off each one systematically, and you're left with no evidence really of any nuclear process to account for the heat generated.
Well,
and
my attitude towards that is that we don't know anything like enough to make statements of that kind. Dr. Carson.
Well, no, I think I think we need an answer, and really need an answer. I think the neutron production is much too small to account for the
Everyone
excess heat.
said that right from the beginning.
Helium
we all
and so
agree
on.
about
So
that.
is there any evidence that the excess heat is due to nuclear processes?
No comment. I don't know.
This is kind of a follow-up on the previous question. I just wanted to point out, we're very interested in the Texas A&M tritium results, and I just want to point out they're not too far off being in line with what would correspond with the heating results of Fleischmann and Pons. Now, Fleischmann and Pons measured tritium and neutrons that was roughly 10 to the 7th to 10 to the 11th lower than would correspond with the heat that they measured. The results of Bockris and Wolf at Texas A&M on tritium were at a rate 10 to the 5th higher. So you're getting in the neighborhood of 10 to the 2 lower than the lowest excess heat. They didn't measure excess heat. It's starting to get in the right ballpark. That's all I wanted to point out.
Well, ladies and gentlemen, I'm afraid we've had a message here which is a kind of force majeure, as they said in France, Dr. Appleby. And the bus is waiting, and we'll leave in 10 minutes. So I'm afraid on that basis I will have to close the session. Thank you very much. Thank you very much for all the speakers and questions.
Hello? Can I ask a question? I'd like to ask... is this going to end?
Right, a rollicking session, right?
The bus coming in and closing it is blockading the road so the troops can't. It's a little bit.
Nuclear fusion, it's what powers the sun. Cold fusion, it creates headlines, and some say it could power Earth's future energy needs. Indeed, 2 months have passed since researchers called a press conference at the University of Utah to announce that they had demonstrated cold fusion. Controlled nuclear fusion, that is, at room temperature, achieved on a tabletop in an electrochemical cell, a test cell containing the metals palladium and platinum immersed in heavy water. Now, scientists from around the world are in Santa Fe, New Mexico. They've come to this, the oldest capital city in the country, a city tucked at the base of the Rocky Mountains and located in a state renowned for its unique blend of culture and cutting-edge science and technology. They're here for a special workshop, the Workshop on Cold Fusion Phenomena, an event sponsored by Los Alamos National Laboratory under the auspices of the U.S. Department of Energy. There are data and ideas to share and discuss, and research directions to chart and clarify. This satellite broadcast is available anywhere in the continental United States. Join us now as the proceedings continue. Let's go live to the Sweeney Convention Center.
Call the evening discussion session to order. If everybody could please be seated. Could people in the back please be seated so we can get started? Well, good evening. My name is Thijs Boer. I'm from AT&T Bell Laboratories, and I'll be chairing your discussion session tonight. This is the second discussion session in this conference. And because of the large variety of topics to be discussed in a true discussion forum, as I mentioned earlier to you this afternoon, and I would like to reiterate this, we have decided not to put up a panel here in order to really stimulate a real discussion among the people in the audience. Nevertheless, in order to do this somewhat in a coordinated fashion, I have asked the speakers of today and yesterday to sit up front here, and if whoever wants to ask a question could once again, this is very important, state his or her name, affiliation, and I was just requested to ask you not to do that until after you have the microphone. The people who keep the records on the side here have no way of knowing who you are and what you said unless the microphone is on. Secondly, as I mentioned earlier, the questions should be brief and short. I don't want any monologues. I think that would not benefit anybody here. Very recent results, sure, you can mention those. I will not, I don't think it's a good idea if any presentations up here. The speakers themselves, in answering a question, can use the overhead, although I try to discourage that, and use the central microphone here. Okay, let me offend that rule right away by showing one view graph for myself, and then I'll throw it open. Just to get you going here. I need your attention a little bit, so that's why I'm doing this. Okay, this is of course completely biased. Some of the issues that I see that we could discuss here, some of them will be very obvious. There are many more beyond this. Calorimetry, the nuclear part, the helium-3, the helium-4 story, what's going on with the tritium, the neutrons, and so forth. I think this, if we use this, we could settle perhaps, at least make a major step forward in the issue whether this whole business is nuclear or not, that is, of the heat generation. Then the latter part, the results a la Jones is the neutron levels at very, very low rates. Are they real? If so, are they cold? Are they hot? What about bursts? And finally, some gas experiments. Now, I will just mention this. And what I would like to do at this point is invite Dick Garvin from IBM Research up here, who will, in his famous fashion, elucidate many of us on some of these issues. So Dick, if you give us a short presentation on this.
Thank you. Now, Brigham Young University, of course, says they have a neutron per second, a fusion per second, and that might even be true. University of Utah said they had heat, 10 watts per cubic centimeter, tritium 100 counts per minute per milliliter, helium-4 1 to 10 parts per million in the off gas, neutrons 4,000 per second. All of those have gone by the board except for the heat. I don't see any reason why I should believe that. Now today I saw some from Professor Huggins, I saw some heat. Some claimed more heat out than there was V times I in. And I might believe that, but even if I did, I don't necessarily believe that it means that one is producing energy. And because the power in is not the average of voltage times the average of current. It is the instantaneous voltage times current, the whole thing averaged over the time of the experiment. If things are on and off half the time, the actual power is double the product of the average voltage and the average current. And so people have to look in more detail into the temporal behavior of their voltages and current. Now, let me point out how disparate some of the other results are. For instance, just take 100 counts per minute per milliliter of tritium in the heavy water, in the electrolyte, just as a standard, with a counting efficiency of 30%, with 10 milliliters, for instance, of cell volume, with the mean life of tritium of 20 years. That's 3 times 10 to the 10 atoms in the cell. If those were created, how did they get there? If they got there with fusion in the usual 50-50 ratio, and the tritium is created in 1 day, then there were an average of 3 times 10 to the 5 neutrons per second for that day. If they were created in a month, there were 10 to the 4 neutrons per second. That's a lot. But when we take the Texas A&M result of 10 to the 6th disintegrations per minute per milliliter, if that amount of tritium was created by fusion in 1 day, that's 3 times 10 to the 9 neutrons per second for that day. And that's an awful lot. That's a dangerous number. So one really ought to be able to look for the neutrons, the helium-3, and so on, accompanying that. And I believe there's tritium there, but I really don't know where it came from. Now let's look at helium-4. Assume you have a watt of electrolysis. That is 1.54 volts times 0.6 amperes. How much helium-4 should you see in the off gas if it all comes out? And if you have as much fusion power going directly to helium-4 as you have power going into electrolysis, a payback of 1 to 1. Well, that's easy. It's 3 volts, 3 electron volts per mole of D2 created. It's 24 million electron volts per mole of helium-4. Equating these two quantities, the power in helium-4, the power in deuterium gas, you find 0.1 parts per million of helium-4 in the off gas if it all emerges from the palladium, and much less if it doesn't. Now finally, the neutron bursts. In the Frascati experiment, in all of these experiments where the counter counts fast neutrons in quotes, but it really counts thermal neutrons which have been moderated by fast neutrons going into the moderator. And it doesn't count thermal neutrons because there's some absorber which keeps them out of the moderator. But under those conditions, the thermal neutrons stay in the moderator and diffuse out exponentially. And so if you see a sharp cutoff in neutron residence, that can't be neutrons. I don't know what it is, but it can't be neutrons. And the last thing I want to say here is the Oppenheimer-Phillips reaction, which has, it's not quite the last, which has been much discussed and is important for below Coulomb barrier reactions caused by deuterons. What happens then is that the deuteron comes in, it encounters the Coulomb barrier, and it cannot penetrate very far without these big exponential factors. Near the nucleus, the deuteron wave function falls off very rapidly. And you can figure because of the energy deficit and the reduced mass of 2 for the deuteron. But the neutron wave function coming out of the deuteron falls off much more slowly, because the binding energy of the deuteron is only this famous 2.223 MeV, and the reduced mass of the neutron is 1/2. So for typical cases, for instance, if you have a Coulomb barrier of 10 MeV, the ratio of these two K vectors, that is, of the exponential close to the nucleus, is 4:1, and it pays you to work on the edge of the deuteron wave function. But for DD reaction, for instance, because the reduced mass of D on D is only 1, and because the Coulomb barrier is only 0.6 MeV, the exponential fall off is only 1.1 for the whole deuteron, and it's 1.5 for the neutron. All of that would be made much clearer except for the stricture against showing foils. And finally, how to obtain these few neutrons? Well, you should remember pyroelectrics. You know, piezoelectrics are okay, but pyroelectrics is where the action really is. And I realize some of you in the audience have worked on this. But a pyroelectric is a solid which doesn't have a center of symmetry. And if one has a phase change from one state to another, for instance, to a cubic state, then the electric charges in the interior are now symmetrically distributed. If you have 10 to the 15 charges per square centimeter, that's about 2,000 amperes per square centimeter that you can draw from one of these things in 1/10 of a microsecond. And the internal fields are 10 to the 8 or 10 to the 9 volts per centimeter. Now, fields don't buy you fusion, just the way the field in the Debye layer doesn't buy you fusion if you have 3 volts of drop across it. And so you have to have 10 to the 8th volts per centimeter times 10 to the times a micron before you can get 10 kilovolts in ordinary DD reactions. So that's where I would look for these arcs and sparks origins when one hydrogenates titanium or palladium and squeezes it or warms it or whatever, and I would listen to that stuff as well as use electrical detectors nearby. So anyhow, that's the quantitative representation of what Thijs Broer told you about some of these problems of the heat, of the tritium puzzle, of the helium-4.
Okay, thank you, Dick. Can I be turned on? Okay, fine. Let me turn on the overhead for a moment. Okay, are there any questions on Dick's talk? It doesn't make much difference on which topic we start here, so the floor is open for questions. Yes, over there.
Henry Randolph, Westinghouse, Savannah Riverside. I'd like to hear from each presenter who described operation of a cell, what they used for poison on the palladium, and what they achieved in loading of D2 on palladium in moles per mole.
You would like to hear this from each presenter? Okay.
Each presenter who described operation of a cell.
Yes. Okay. Who of the presenters would care to answer that question? Steve Jones.
I need a mic.
Oh, yes. Yes, that's right.
In fact, is this on? In fact, I think in my talk this morning I said if anyone wants to ask this question, you may. So thank you very much. I would really like for others to start looking at the Brigham Young type approach here too. So I've prepared a few things to talk about. First, I would say I'll discuss this in a little more detail as I go along, but one suggestion would be to read the published paper, since there are some changes from the preprint that many of you have read. Okay, now the requirements, of course, requires a fairly sensitive neutron detector. That's clear. And pardon? I'm coming. Next step. You got the detector. You want me to go on to the next? All right. But let me point this one thing out. If you want to look at bursts, which I think are fascinating, you've got to be able to handle something like 100 neutrons in a very short time and be able to not be just wallowing in dead time. All right, cathodes, here we go. Our cathodes, as described in the paper, are fused titanium. And let me start with titanium. What we've been using up at Los Alamos the last while is this type of a mixture. We take titanium and palladium powders and sinter them or fuse them at 900 centigrade. Roughly 80% by weight of titanium, 20% by weight of palladium. Now, in our paper, we talk about fused titanium. This was commercially purchased, and I think the company was Fisher Scientific. In any case, I've looked, and I can't find a company that makes this material, so here's another way that Tony Mayer actually developed at Los Alamos to build these cathodes. Is that enough on that? Sanded foils, yeah.
Argon atmosphere.
Could you hang on a second until you have the microphone?
Yeah, the question was the atmosphere. These were prepared in sort of a funny way. These were just prepared in air, which means there's a lot of oxide, and perhaps that's important. When you have palladium on titanium, it has been determined that even with an oxide layer, you can get through that with the palladium on the titanium. That's the way Tony did these, and of course we would like to do some in a vacuum, and maybe argon is a good
But you have not done that.
We have not done that as yet. The fused titanium, I don't know how Fisher did those, but probably something like that without the palladium. The foils that we've used, palladium, and again, we've not used rods at all. We go to the maximum surface area to volume possible. For the foils, recently, this is where we saw the burst, is when we had this fused titanium material and zirconium and vanadium foils, which had been sanded. We always roughen the surface as much as we can. But in the paper, we had talked about palladium foils sanded to roughen the surface. Cathodes are there. The electrolyte, we started with this Mother Earth soup. And I like that. Again, I owe that to Tony Mayer. It came from geochemical considerations, so that's a good way to say that. But we then started looking at a little palladium chloride and lithium sulfate. And then finally, the runs where we saw the burst, we were just using lithium sulfate in the electrolyte solution. pH 3 to 3.5. Excuse me. Too much of that good food over there. D2O. Course, and there's the purity level that we used. Temperature was about 26. We measured occasionally the temperature with the thermometer. Recently at Los Alamos, we've been trying to cool our electrolyte. As Howard Mallove mentioned, we're seeing these bursts at around minus 30 centigrade. We've seen them at other temperatures as well, but this seems to be an interesting temperature, and so naturally we would like to see if we can operate these cells as cold as we can get without freezing the electrolyte. And perhaps we can do that. We were trying a liquid nitrogen bath with the vapors cooling the cells. Time duration is important. We think that we start seeing things after about an hour, and look for a few hours, 5 hours say, and then start again. These bursts, however, those cells we ran for many days and just let them run. And again, after we turned the voltage off, we still saw spikes. And the point there is that the conditions are not equilibrium even when the voltage is off, because the deuterium is still moving in the lattice and so on. We have not seen spikes, however, when we have no cells there.
Okay, thank you, Steve. I don't want to cut you off, but is there anybody else who cares to comment on this poisoning effect, perhaps? Yes. Could you hang on until you have the microphone? Thank you.
I had a question for you.
Okay, I'm sure.
I'm going to set this up there so you can read it while I'm answering Bob's question.
Robert Sherman, Los Alamos National Laboratory. Steve, my question with regard to your, quote, Mother Earth soup.
Yeah.
In your paper, you give a composition. Is that the order in which you attempted to dissolve all of these things, or is the order actually different from that?
Good point.
Or did you mix them all in small quantities and then pour them together? and you mention a pinch of gold cyanide. Can you quantify that?
Yeah. Okay. Thank you, Bob. First of all, the order was done at random, and we pour off the clear fluid. We do not try to stir up and get it does not all dissolve very well. That's a good point. The second thing is that, and again, we're not using that Mother Earth solution so much anymore. Let me see, the question about the gold cyanide. This was a standard solution for gold plating, Bob, and we used a very small amount. It was about, let's see if I can remember the gradations on the pipette. I think it was about 0.02 milliliters, just a small pipette, and standard solution for gold plating.
Any others? Yes, up front here. Could you get a microphone up here?
Laszlo Ridi from the Argonne National Laboratory. About the poisoning effect. We didn't use any poisons or additives in our electrolytes. It was a lithium deuteroxide saturated heavy water. And we were able to reach the 1-to-1 palladium deuterium composition. We actually didn't see any excess heat. But my answer is a little bit of question. Whether the poison is really important. We heard many things about the poisons, but I wonder who saw excess heat really are using poisons. If they are using, why then they do not disclose it, this kind of thing. And one hint about the poisoning.
Yeah, we don't see any excess heat, so you'll have to ask that.
Yep.
No, but relative to the poisoning effect, I raised the question that is it really important? I suppose that poisoning would promote the palladium deuterium ratio increase, and if one can reach that ratio without poisoning, whether the poison is really important. But the comment on the poisoning can be that certain poisons or additives may set up a corrosion, a reaction which may produce excess heat. I do not suppose that in the 20% range, but in a certain percentage range, they can produce an excess heat. So I would ask another question to those people who have seen the excess heat, whether they are using poisons or not.
Yeah, there's a question or a comment on that over here.
There's a speaker's name. You said it before.
Yes. Yeah, once again, I would like to stress that please state your name and affiliation after you get the microphone. If people over there go haywire, they have no way of keeping a record of it.
So my name is Laszlo Ridi from the Argonne National Laboratory.
Thank you.
My name is Nate Hoffman from ETech Rockwell International. Question with respect to poisons. I've examined electrodes that have exhibited some results. In every case, I've always found needle-like growths after the electrolysis, and those needles have been capped with iron, whether iron was deliberately added or not to the solution. And one of the thoughts being that these needles might prevent the proper amount of overvoltage, and that by being capped with iron, you help allow an adequate overvoltage to get the deuterium in. So even if you didn't add iron as a poison, it might pay to look for it with SEM and EDAX. And I know that at BYU at one time you felt it important to always add a little iron. And then,
titanium cathodes.
And then the second additive that I think is critical for everybody to pay attention to, if you sparge your electrolyte with deuterium gas, you normally will up your tritium level up to anywhere from 1/10 of a microcurie per millimeter up to 10 microcuries per milliliter, which is 1,000 to 10,000 times more tritium than would be present in normal heavy water. So one additive that should be watched very carefully is any spurging with deuterium.
Okay. Is anybody who cares to comment on, perhaps on the, among the electrochemist group who could, yes, right up here, on this poisoning issue?
Well, I'm Srinivasan from Texas A&M University. Dr. Appleby made the first presentation, and this was using our microcalorimetric technique, where we were able to show excess heat for the system PD-LiOD, really. We did not see the excess heat with PD-LiOH or PT in LiOD. Now, we had carried out our measurements in a stainless steel cell. This was because for better heat conduction, we used the stainless steel cell. And this was, our electrode samples were analyzed by Nate Hoffman, and I think he mentioned to us that he saw some chromium, some iron, and so forth. So we intentionally did not edit, but these would increase the hydrogen overpotential. And according to what Fleischmann and Pons had told us also, it could be that if you increase the hydrogen overpotential, it could help the entry of the palladium into the metal.
Okay.
Now, we did not make any measurements of the hydrogen content directly in our small samples. Okay. I would also like to add one more point here. We had seen excess heat up to about, say, 20 watts per cc in the samples like 0.5 millimeter wires, 1 centimeter in length. Now, we wanted to look for helium-4 or helium-3 as well as for tritium in the sample. Lawrence Livermore did the analysis for helium-4 as well as for the helium-3, which could be produced by the decay of tritium, which they could analyze with their mass spectrometric technique, and they did not find helium-3, nor did we find helium-4. Thank you.
Well, I think that's a very interesting result. Somebody in the back there who wants to comment on that, or perhaps make another comment to the on the poisoning effect? Let's take that one over there first.
Vittorio Perdo from Devonville. Actually, I wanted to ask a follow-up question on the results on Texas A&M just brought up about the helium. It was my understanding, I think this is what I just heard, that no helium was detected. From the tritium concentration, the neutron concentration, one can calculate maximum possible heat generation rate attributable to fusion. And please correct me if I'm wrong, but it doesn't come anywhere near the energy generation rate reported by Texas A&M. I guess my question to anyone at Texas A&M is, do they feel that that disproves the claim that the heat generation rate is attributable to fusion?
I think that's a very good question. Somebody in the Texas A&M crowd cares to answer on that? Yes, up here.
At the moment, I would say we are not ruling out anything. The reason being that we think that there could still be a chemical explanation for our heat. The one way that we will try to show that there could be, say, for instance, recombination is by carrying out our calorimetry experiments in a closed cell. Now, there is one other possibility. We think that the lithium plays a critical role in our measurements. Because, say, for instance, when we transfer from LiOD to NaOD, there is no excess heat generation, or it falls off considerably. Now, could there be some type of a surface reaction which involves lithium, and we'll say deuterium, which could still produce, say, for instance, tritium or something, which we will still have to measure. So we are going to do an experiment now, starting with Li6, really. Oak Ridge National Lab will be giving us some Li6. And because the relative abundance of the Li6 in the normal lithium is only about 6%.
Quick follow-up.
Okay, yes, yeah, go ahead.
It's my understanding that a lithium reaction would necessarily involve either tritium or helium, and that the tritium amount was measured, and I accounted for that, and the helium was looked for and not found. So wouldn't that rule out fusion?
The thing is that I don't think this is
yes, it's okay.
Okay, thank you. With respect to the tritium measurements, we have some anomaly. I mean, in the sense that we don't find any tritium in the metal as such. Now, from Professor Bockris's group and Dr. Kevin Wolf, I think, may follow up, they have measured tritium in the electrolyte. There is one thing which I would say about our electrolyte samples. We probably have not waited long enough, or I don't know why we could not measure tritium in the electrolyte so far. But there is another possibility that if it is an Li6 plus D2 reaction, it could produce helium-4, and that may not stay within the metal. So we have not analyzed for helium-4, say for instance, in the solution or the outgoing gases.
Okay, Professor Wolf.
Kevin Wolf, Texas A&M. The question on energy balance with these high tritium yields, we're still many orders of magnitude off, so I guess you know that. Let's see, what else did we have? Also, I should qualify it that we're still looking on to the tritium as to the source, since you don't know. Okay. I had one.
Okay, go ahead.
I had one comment long ago on the poisoning. And the iron thing people are talking about, there may be something there.
I can't hear you. Okay. Could you speak up somewhat?
The comment on the poisoning. We did a K-X-ray analysis on the solution from the one cell we had at the Cyclotron Institute that produced both neutrons and tritium. And we do have an appreciable concentration of iron in that, even though we didn't add it. You know, it came from somewhere, a heater and a calorimeter or something. So it seems like the iron thing is maybe a common thread. That's all.
Was it a question or a comment over there?
Yes. Ernest Rogers. A dumb question for a physicist to get an answer from chemists. About poison, or maybe a better term would be seasonings. I'm under the impression that chemists never keep alkaline solutions in glass containers. Isn't that right?
One of the chemists cares to respond to that?
That's what it's
over there.
Hello? I'm Howard Rogers with Hughes Aircraft. Goes back a long ways on keeping of basic solutions, either sodium or potassium hydroxide, in glass that invariably freeze glass stoppers because it forms a silicate, which then forms a continuous glass. So the answer to that is definitely, if you knew what you were doing, you wouldn't use glass.
Okay, thank you. There's a question up here.
Coming back to the issue, chemical or nuclear energy, I would like to point to the particular last experiment reported by Dr. Appleby, that there seemed to be an effect, an isotopic effect on the amount of energy produced in these cells. If that were to be confirmed, it would be extremely difficult to explain this as a chemical effect. An isotopic effect on the amount of heat produced in the cell was reported. He used lithium-7 natural and lithium natural and lithium-7. And there was a difference in the heat production of the order of 20 or 10%, if I remember correctly. That, for me, is very difficult to interpret other than in nuclear terms. But I wouldn't use the word fusion. Okay?
Somebody cares to comment on that? I know there are other people lined up, but I want to get this straightened out here. Steve Koonin, could I have a mic here quickly?
It's very short, so let me ask it directly.
Wait, just hang on a second. Hang on a second. Wait for the microphone, Steve.
We don't know who you are. Steve Koonin from Caltech. Why is that any harder to understand than the difference between hydrogen and deuterium that Appleby showed us?
It is not harder to understand, except that if we think of deuterium reactions, we have excluded these in terms of the helium observation. While if we think in terms of some isotopic effects, which include transfer of neutrons, which have been discussed.
Okay, so one is just retreating to a corner in the
No, I'm not retreating to a corner.
situation.
I can give you an example very clearly, which has been already mentioned by someone, I think, and I may have mentioned in an earlier discussion, which was the lithium-DEP reaction.
Those of us who have calculated fusion barriers,
we
as
know
you have,
all about it.
you know,
we know all about
if you thought DD was hard, why do you try
Yes.
lithium D?
Say it again, please, Steve.
If you thought DD was hard, why do you try lithium D?
Okay, perhaps we could move on. Somebody up here has been waiting for a long time.
Shimshon Goddesfeld, Los Alamos National Lab. First of all, a short comment about the poisons.
Yes.
People here are warning against poisons, but the thing is that it is a spiral. I mean, the counter-argument is always, maybe you want the poison, all right?
That's
and
right.
so, you know, you can't really get out of that. In other words, maybe you want to use glassware, maybe you want the silica. Right now, we're not in a position to tell whether silica, or for that matter, any poison, helps or does not, or works against you, okay? That's comment number one. Now I have a question to Bob Huggins. I haven't heard anything from him about the mode of preparation of the palladium, and I'm very curious about it. I heard warnings against graphite. What is he using for a crucible, please? And what can he tell us about the general protocol for the preparation of the palladium?
Bob Huggins is sitting over here.
Yeah. With regard to poisons, we don't know that we have any, but we might. We prepare our material by taking an old crucible that was purchased several years ago by someone else from Engelhart. We remelt it in a arc melter containing argon, 1 atmosphere. We pre-melt titanium with this arc melter to gather the argon. We then arc melt the palladium, about 1 to 2 grams at a time, on a cold, water-cooled copper hearth. You melt the top 2/3 of it, then you turn it over and you melt it back again, then you turn it over and you remelt it, then you melt it back again, and then you flush out your argon, then you refill it with argon, you remelt the titanium to gather the oxygen and nitrogen out of the argon, and you do the whole thing 10 more times. We don't know what we do that helps.
Bob, if I may interject one thing. I talked to one of your metallurgists, and I believe that in your arc melting furnace, you use what the metallurgist described to me as a tungsten consumable arc melting furnace. And it was their impression that you, in all likelihood, have some amount of tungsten. In addition, as you just mentioned, the crucibles that you used were apparently used, but correct me if I'm wrong, some years ago for melting of lithium and potassium materials. Is this true? Could you perhaps, I mean, this may or not be relevant, I don't know.
Yeah, it may or may not be relevant.
Right.
The material we use is a crucible of what was known as nominally pure palladium, which we used in our laboratory for transporting hydrogen through it using molten salts of lithium chloride, potassium chloride on both sides. We transported hydrogen back and forth through it. So we knew it had a lot of hydrogen in it when we remelted it, and of course we saw lots of nice bright red lines in the emission spectrograph, in the optical emission. Was there a further question?
No, I think that's it.
Yes, this arc melter has a water-cooled tungsten tip on the top of it. The bottom of it is a water-cooled copper hearth.
Okay, let me, a gentleman up here is waiting for him.
Bob Sherman, Los Alamos. I have a question relative to tritium production of Professor Bakris. You stated earlier today that there were at least 3 other groups that are reporting tritium production in their electrochemical cells, and would you care to elaborate on that and name the groups?
Somebody cares to answer that on that one, on the tritium? Yes, back there. Okay, right.
See, I'm Ken Wilson from Sandia Labs. The 3 groups, as far as I understand it, well, we saw some evidence of tritium reported by the University of Rome in the poster session behind the screen. University of Florida reported tritium in the newspaper several weeks ago. And Pons and Fleischmann, of course, had low levels of tritium. And there was one Korean group that I've heard at this meeting mentioned as reporting tritium, as well as the Texas A&M group.
Okay. Oh, I have a microphone there. I'll be right. Okay. Yes.
Yeah. My name is Gordon Michaels from Oak Ridge National Laboratory, and my question is to Dr. Appleby about the helium concentrations that were measured. In your chart, you show helium concentrations for both the controls and the test samples for helium-3 at about 1 billion. which is presumably your accuracy of the measurement, and in helium-4 for about 10 to the 8th atoms for your samples. My question is how many helium atoms were you expecting to see? You know, we've heard results where people have been reporting 1 neutron per second rates above background, and there's been inferences that may be fusion. If you were creating 1 helium atom per second, you wouldn't create anywhere near enough helium to be able to measure it within this detection accuracy.
That's the limit.
Anybody wants to answer that? Just a minute.
I don't know, is there somebody from Livermore here who could answer that question? Yeah.
Yes.
Actually, the measurements were done by Brian Oliver at Rockwell, and...
Oh, yeah.
Okay. Hi, it's Brian Oliver from Rockwell.
I'm sorry.
I didn't mention you. It's all right, Srini. We did the original measurements of the helium in both the Barcarus and the Appleby palladium. And I believe Los Alamos has repeated the helium measurements, or Lawrence Livermore has repeated the measurements. What we measured in the palladium samples for both groups was essentially the background levels of our system, which conservatively is about 8 times 10 to the 8th atoms of helium-3, and I would say about 5 times 10 to the 8th atoms of helium-4. And if, in answer to that other question, if you were expecting watts per cc of cold fusion producing 4 helium, and that's many, many orders of magnitude less than what you'd expect. Now, I'd like to make one other comment. The tritium measurements in the Barcarus samples are very interesting. We did not see any helium-3 in the palladium in the Barcarus samples, but myself and Ken Wilson have spent the last 24 hours looking at this, and we basically concluded that given some basic assumptions that were, in terms of time that the tritium may have been produced, our detection limit for the helium-3 would not contradict the tritium levels that Barcarus is seeing in his electrolyte. In other words, 10 to the 6 counts per milliliter per minute would probably have produced helium-3 levels in the palladium, which would be just at our background uncertainty in the mass spectrometer system. So we don't contradict the Barcarus data in terms of the tritium. Okay.
It was just suggested to me, and I think I almost forgot about it. The people in the front row can certainly use this microphone that frees up at least 1 or 2 microphones. So let me ask the next question. Let's pass it along to Dick Garwin.
Dick Garwin, IBM. 2 things. 1, the helium-3 that corresponds to the million tritiums per minute is 10 to the 13 or 10 to the 14.
Oh, yes.
But the question I wanted to ask is, why do people keep talking about dilithium? Because the reduced mass of the proton against lithium-7 makes that exponent only half as big, 100 orders of magnitude more probable to have p-lithium-7. But before you get your hopes up, p-lithium-7 going to helium-4 plus helium-4, no radiation. Well, you heard about the knock-ons, the deuterium knock-ons, which will give you plenty of everything to count.
Yes, back there has the microphone, right?
My name is Tom Walters. I'm from Westinghouse, Savannah Riverside. On somewhat of another topic, but somewhat related to what was said over here, there have been many suggestions that non-equilibrium conditions are necessary. Right. Words like, excuse me, words like phase change have been mentioned. And I've seen only one poster session that has attempted to look at the microstructure of the cathode after it had been electrolyzed. Since large volume changes are associated with the hydrogenation of palladium and concomitant elastic stress in this material, I was just wondering if anybody had thought to characterize their cathodes by microstructure analysis before and after any possible observation.
Okay. You had a question. Did you want to comment on this, or?
No, just a question.
Okay, is there anybody who wants to answer or make a comment on this particular question before I go to you? Perhaps you can hand the microphone back. Thank you.
Yes, I'm Lauren Fuller from the Oak Ridge National Laboratory. I don't know whether you saw our microstructures back here in room 6 or not. This is one of the strong aspects of our program that we're working on right now. And yes, there are fascinating things happening in the hydrogenation-dehydrogenation process, going along with your comment. If you have any other specific questions, see me and I'll be glad to discuss those with you.
You can use the microphone. A comment up here on that? before I get to you up here.
Tajima from University of Texas. If there is a local large electric field generated by perhaps phase transition or any other local incident, then such a large electric field could induce what we call the optical phonon instability, which can enhance the either energetics of the deuterons or density of the deuterons, which could induce a large amount of fusion.
Optical phonon densities, that's being a solid state physicist triggers me. That's new on me, but anybody cares to comment on that? Perhaps we should move on. I know Stephen has been waiting for one. Perhaps you could use the front microphone, that clears one up.
Well, I have a question.
Okay.
Stan Luckhard from MIT. You know, my question is about the measurement of excess heat, and also, you know, the statement in the Pons-Fleischmann paper that it's inconceivable that this amount of excess heat could be anything but nuclear process. So I did a calculation where I divided the reported excess power by the cell current times 1.54 volts, which is the, you know, the chemical power being released in the reaction, and it's always less than 1 or of the order of 1. So it seems to me that that excess heat is really of the order of the chemical power of the only reaction I know about in there. So my question is to Professor Huggins, and it's about the error bars on the calorimetry and about how strong this claim is that you actually see power greater than you know, than really the cell current times the cell voltage. And the other part of the question is, we've always thought it was pretty important to look at the time evolution of the cell voltage and cell current as you're doing the experiment. And I noticed that the powers are like 10 watts and 15 watts. It seemed like you may have a very unusually high cell voltage there. So if you could answer about that.
Yeah, I think that's an important question. So I know that people are waiting here, but let me give Bob Huggins a quick chance to rebuttal on that. Can we get a microphone? Bob, you can come up front if that's it'll be faster.
Yeah, you asked about precision. We've made 5 different modifications of our system, and we now have a precision that's well within 1% of the total power that we're measuring. We are seeing excess power above and beyond the product of externally applied current multiplied by voltage that yesterday was 12%. If you also subtract out the 1.53 volts, 1.54 volts, then you get a larger number. But we do not choose to do that. We're using a very conservative number. So we are confident that we are seeing at least 12 times as much excess power as the resolution of our measurements.
May I interject something here? To understand that correctly, when you do the entire energy balance from T equals 0 when you turn the cell on until you're done, and you add it all, I mean, you accumulate your measurements, and then you still have the 12%, or perhaps
no,
that was not clear to some of my colleagues.
Yeah,
who know that.
I'm talking about the power ratio, power out to power in.
Okay, but on
now if you do it on energy, it depends upon how long you run your experiment.
But that's important.
Well, we haven't run an experiment as long as we can to see when it dies, if it dies ever. We have run experiments that are well beyond a factor of 100%. At the beginning of our experiments, we see the endothermic effect, which you expect for the electrolysis of the water or D2O. As the experiment with hydrogen, light water, continues, nothing changes. As the experiment with heavy water continues, the amount of heat gradually increases, and after about 2 days, you come out even. So the amount of heat generated somehow by some process inside the material is about equal to the endothermic heat, the refrigeration heat of the electrolysis process. After 5 days, we're well beyond that, and we have real live excess heat coming out in the form of power. Now, we have run for 5 or 6, well, as of yesterday, 5 days. The total amount of energy, which is power integrated over time, total amount of energy is greater than that went in. But the first part, of course, is an investment. At the beginning, you have an endothermic effect. So for a couple of days, you're on the negative side of that energy balance. But we're beyond that, we're on the positive side. We have no idea how much longer this thing is going to work. The longer it works, the more positive the energy balance is. Okay. But the power balance is always positive.
Right. The person has been waiting for a long time, but Steve, if you have a 5-second interruption. Just a minute, hang on. The microphone quickly here, please.
It's directly relevant to this. Steve Koonin, Caltech. Yes. I didn't hear you say the number that I had hoped you would say. Take your best cell for the longest time you've run it, net power out divided by total power in. Net energy out divided by total energy in. Yeah. What is that?
Steve, the cell we're running right now is the cell we have all these very careful calibrations on, and we're something like 120% energy out to energy in. But there's no reason to think it isn't going to get longer, smaller. We don't know. Our experience is that these things keep on going. But this particular one, which I showed the data for today, which were very firm data, is still going.
Okay, let me hand it over. A question or comment over here. Been waiting for a long time.
Yes, my name is Ali Abutaha. Yes. I'm from Reston, Virginia. And my question is a follow-up, actually, to the last 2 questions. My question is to the speakers who had conducted calorimetric experiments and measured excess heat or did not measure excess heat. The question is this: did any of them measure the strength, for example, the ultimate strength of the palladium sample before the calorimetric experiment and afterwards? Previous data shows that there will be a difference in strength. That difference in strength, which is stress, can be converted to force, and through proper mechanics, one can introduce the distance, calculate work, convert it to heat, and it comes out in the order of megajoules per centimeter cube, which seemed to be the essence of this whole paradox. So to go back to the first question, was the strength measured before and after, or are there plans to do that in the near future?
Okay, let me, if I may interrupt here, because there are some people waiting in the center there. Just to comment on that, it appears to me that regardless of the details of that, there's no way that any classical process like strength is going to get you into the megajoule regime. Not easily. I mean, megajoules is real, and a nuclear process seems one of the few things left. But the person there perhaps might make a comment on that.
I'm Colorado State.
Just hang on. Could you state your name, please, and your affiliation?
Yeah, it's right. Does it work? Yeah,
yes, it is. Yes.
Peter Hochheimer, Colorado State University in Los Alamos National Lab. I'm a solid-state physicist, and I try to minimize my confusion. So I have a couple of naive questions, and one of it is, how does it come that you get such different numbers for the DPD ratio? And how is it measured? Because I know from my experience that when you take this stuff out, you load it above 80%, you have diffusion at room temperature, and you lose it again. So I would really like to get some information how these numbers were determined, and what are the real numbers? What are really the numbers of these ratios?
I think that's an excellent question. I mean, that's, hang on a second. Okay, let me come back to that in a minute. This is a very important issue. I know I've made this the important thing in my own measurements also, the accurate measurement on the DPD ratio, preferably, of course, in situ to the experiment. And there were some speakers this afternoon, I believe it was, suggesting some impedance measurement. That's a very nice way, but perhaps somebody cares to answer on that. I forgot who it was, on the accurate measurement, because this may or may not be critical. Is there anybody who cares to comment on the measurement? Yes.
I have a question for Professor Huggins, but I can also respond to the impedance too.
Why don't you do that first?
All right. Bill Ayers from Electron Transfer. We have a poster on impedance measurements of hydrogen deuterium content in palladium, and it's a fairly easy measurement to do. DC resistance measurements have been done for years, but the AC impedance measurements can show you more detail, including saturation and some strange non-equilibriums before you reach saturation, also if you reverse current. So I would recommend people try to do impedance and correlate that to weighing or degassing or ideally neutron scattering.
Yeah, a question, a follow-up on that?
Yes.
Right.
We've been doing it.
State your name and...
Shimshon Goddesfeld, Los Alamos National Laboratory. We've been doing recently, actually we described on a poster, some full-probe DC resistance measurements on palladium. And it's a very simple measurement to take. These are a few milliohms that you measure, and it changes as you load it up to about palladium H sub 0.7 or so, or D sub 0.7, changes by a factor of 2. Then what is expected, according to reports in the literature, is that if you are able to charge it to very extraordinary levels, close to 1 D over palladium, the resistance should start coming down again. And we never saw that. But that doesn't mean very much because we didn't use very high current densities. Anyway, the measurement is doable in situ, and I think it's quite informative.
Okay, thank you. There was a... just hang on. Just a minute. Can you use the microphone with the... which is still... Okay. Hang on a second. Can we get the mic... Can we easily get a mic back there for the follow-up there? Right in the center here. It's an unfortunate location.
Yeah, so it's secure that one can account that numbers of 1 have been reached. Occupation number of dP is 1.
What? No, I said rather to the contrary. Not in this particular experiment that we measured. Doesn't mean that you can't reach.
Somebody reached that number?
Well, people have reported something based on gravimetric measurements earlier today. Maybe they want to comment on that.
Yeah, but that's not reliable or what?
I think you're correct. I think I heard one person quoting 1, but by and large, the number is 0.7, 0.8. I think that's correct. Over there, let me.
I'd like to ask a question on another subject that was brought up by a remark made by the gentleman from Rockwell, who said that if you scrubbed heavy water with deuterium gas, you would transfer a lot of tritium to the heavy water. Now, what's the source of the specific activity of the tritium in the deuterium gas, which would be higher than in the heavy water, unless the deuterium gas has been exposed to a high tritium source?
Okay, could I get one microphone up here, but I want to take a question first up here.
Well, I'm the guy, I'm also the guy he's asking the question of.
Okay.
But I first wanted to respond to the business of how much deuterium you have in palladium, if I can.
Yes, go ahead, but try to keep it in context. I know it's difficult. Go ahead.
Okay, my name is Nate Hoffman, E-Tech from Rockwell. The business about how much deuterium in the palladium, the only way that we've found that we think is accurate is to measure the volume of the gas that you release at the instant you stop the electrolysis. You measure the volume at 1 atmosphere of deuterium pressure, and you know from thermodynamics what is the amount of deuterium in equilibrium at 1 atmosphere pressure, and you add the difference that you've collected. We don't like weight measurements because we find there are impurities of iron and platinum and other things that go on the palladium, which you can wash off, but it would still give you a higher ratio than you should get. When we load the things up above 0.7, we get extensive surface cracking. This cracking, I think, interferes with resistivity and possibly impedance, so I'm not sure of that. We haven't tried that. But since surface cracking occurs, you have to be aware of that if you're trying resistance. The business about the deuterium versus heavy water, because tritiated water is very dangerous as compared, health-wise, as compared to the gaseous form. People take a lot of care to get the tritium way down when you have heavy water. That kind of care is not taken with deuterium gas. I believe in Darlington, for example, they're allowed to release 7 times 10 to the 7th curies per week of deuterium gas containing tritium gas. And for tritiated water, the level is far, far, far less than that.
Yes,
because of that, deuterium gas has tritium in it because it hasn't been taken out to
Yes, but the specific activity of deuterium gas, which is in contact with water, is either equal to or less than that of the water. And the only way of reducing the tritium in the water is to put it through an isotope separation plant and detritiate it. There are plants that do that.
The deuterium that's coming in is higher in tritium to begin with, so it gives some of it off to the water as it bubbles through.
Okay. You've been waiting for a long time.
Dick Crooks, MIT. My question is for Professor Huggins. So the claim that was just made that the net time integrated energy balance is greater than 1 in his cell is an extremely important claim, and as far as I know, the first claim that an energy balance has been greater than 1. So my questions are 2. First, can you explain exactly how you've done your calorimetry? And second, can you substantiate your claim by showing us voltage and current histories for the cell that has demonstrated this net energy balance greater than 1?
Once again, could Bob Huggins comment on that before I continue with up front here? Use the microphone up front here. That's probably be the easiest.
Yeah, I discussed this afternoon the details of how we do this, and I would rather talk to you privately rather than repeat it for everyone, because these people obviously heard it with great level of detail this afternoon. What we're saying is when we have had these cells in operation for a long enough period of time, their heat output gradually increases with time. And after a while, the total amount of heat out, which is energy out, exceeds the investment you made at the beginning of the run. Now, we have in no way found how far this can go, but we're convinced that the